Hi everybody. So in this lesson we're going to look at how to apply a modified Newton's method to find zeros for functions that have roots of multiplicity 2 or more. So let's recall this. If we have a function f of x and we want to solve f of x equaling 0, now remember that Newton's method states that we can use this function as an iterate. So if we look at this function, what we can do is use this function, we'll call it g, and we can iterate it. So suppose that our solution to this problem right here is x equaling p. What we would do is take a guess, try to get close to p, put it into our function g, and just iterate it. Now that's Newton's method. Now that works well if the 0 to this function up here has is of multiplicity 1. Because if it's of multiplicity 1, then what that means is that the graph of f crosses the x-axis in this manner, transversely. So in other words, the derivative right here is not equal to 0. Now if your 0 were to look something like this, then you would have a root of multiplicity 2 or more at p. Then Newton's method doesn't work very well, because when you start to apply Newton's method, drawing tangent lines and finding where they cross the x-axis, they sort of get trapped in this region down here and result in slow convergence. So what we're going to do is we're going to modify this function right here to try to make Newton's method work better for roots of multiplicity 2 or more. So what we're going to do is this. Instead of considering the function f of x and applying Newton's method to it, we're going to consider this function. We're going to consider the function u equals f of x over f prime of x. Now, if we look in our text, right here is that function that we're going to be considering, and we're just going to follow down through the notes here to see what's going on and what formula we eventually end up with. Now, notice this. I claim that if the function f has a root at x equaling p, and suppose it's of multiplicity 2 or more, then I claim that the function u also has a root at p, but it's only going to be a multiplicity 1, and so we're going to apply Newton's method to this function instead of just f. So in other words, I claim that u of p will still be 0, just like f of x, f of p is equal to 0, but I claim that the solution to this is a root of multiplicity just 1, and then we'll be able to apply Newton's method to this function up here. Now to see why that is true, if f has a root of multiplicity m, then what that means, recall, is that we can write f of x as x minus p to the mth power times some function q of x, where the limit as x approaches p of the q does not equal 0. Okay, so that's what it means to have a root of multiplicity m. Recall that, if I have a function like this, f of x equals x minus 2 cubed, this function has a root at x equaling 2, and it's of multiplicity 3. Alright, in this case our function q would just be the number 1. Alright, now let's show that u only has a multiplicity 1 root at x equaling p. So given that this is the form that our function f takes, if we plug this into here for the f, and then we take its derivative and we plug it in the denominator here, let's see what we get. Now that's illustrated over here. So right here we have the function f, and right in the denominator I claim that this is f prime right here. Now what we're going to do is simplify this and prove that u has a root of multiplicity 1 at p. Alright, now notice that, how did we get the denominator here? Well, if we go back to this function f right here and I differentiate it, just notice that f prime is equal to x minus p to the m. We're just going to use the product rule here. It's going to be x minus p to the m times q prime plus the derivative of x minus p to the m is m x minus p to the m minus 1 times q. Alright, so there is our derivative for f, and we plug that in to the denominator here. Okay, so right here it is. And now what we do is we're going to simplify this and show that u has a root of multiplicity 1 at x equaling p. So if we simplify this here, you notice that I'll just fill in one step here. What we do is in the denominator we factor out an x minus p to the m minus 1 power. And when you do that, you get and what you're left with then in the denominator is just m times q here plus x minus p times q prime. Now you notice that we have some cancellation here. This term cancels with all but one of these terms up here. And then what we end up with is this down here. So that's exactly what we end up with. Now notice that this term right here is our, notice that we can write this as x minus p, and now this is a new q of x right here. And notice that we have a 1 right here now. Okay, so now note that if I put p in for x here, this term of course is 0. And if I put p in for the x's right here, I get back 1 over m. So you notice that u of p equals, this term is going to be 0 times, and when I put p in for the x's here, you notice this term goes to 0, because when I put p in for x here, I get 0 times q prime of p, and I get 1 over m, which is 0. Okay, so u does have a root at x equaling p, and you'll also notice that if we take a look at the limit as x approaches p of the new q function, capital Q, if I put p in here for x as I just stated, we get 1 over m, which does not equal 0. And so therefore u has a root of multiplicity 1 at x equaling p. And that's good for Newton's method. Roots of multiplicity 1 work very well with Newton's method. So now what we're going to do is we're going to apply Newton's method to the function f of x divided by f prime. And now we have to figure out what Newton's method becomes when we do that. Okay. So now taking this function right here, we have to apply Newton's method to it. So what we have to do is evaluate x minus u of x divided by u prime. of x. Okay, so this becomes, when we do that, we get, now the u is going to be f over f prime, so I'm just going to write that as f over f prime. Now in the denominator, we have to use the quotient rule here. So when we do the quotient rule, remember bottom times derivative of the top, so we're going to get here there's bottom times derivative of the top divided minus top times derivative of the bottom, and then divided by the bottom squared. Okay, so we have this big fraction right here. Now what we're going to do is we're going to take this fraction here and just flip it and multiply it against f times f prime. And what we end up with is this. Okay, so I'm going to get f over f prime times, and when I flip this, we're going to get f prime squared divided by now you notice the f prime here cancels with one of these f primes right here, and we end up exactly with this formula right here that is in your text. So this is the modified Newton's method now for functions that have roots of multiplicity 2 or more. Now you notice what we have here, we have to take the second derivative of f in here. The original Newton's method only had f and f prime. Now the modified method down here has f prime, and f double prime in it. And so if we're given a function that has a root of multiplicity 2 or more, we just have to take f prime, f double prime, plug it in this formula, and iterate it. And that's it. That is our modified Newton's method. Now let's take a look at a quick example here to illustrate this, how it works. So let's start out with this function. I'm going to make a new screen here. So consider the function f of x Now this function I claim has a root at x equaling 0, p equaling 0, and it is of multiplicity 2. Let's verify that. Alright, now if you recall from your text, going back to a previous theorem here, I'll just write here. This is our theorem that tells us how to find, or how we prove that a root is of a certain type of multiplicity. If we want to show that this function has a root of multiplicity 2, we need to show that f of 0 is equal to 0. Now that's my p. Okay, or let me say it like this. We need to show that f of p is equal to 0, f prime of p is equal to 0, and f double prime of p does not equal 0. This will show then that the function here has a root of multiplicity 2 at p. If it were going to be a root of multiplicity 3, then we would need this, and then f triple prime of p does not equal 0. This would show a root of multiplicity 3. And that is all discussed in this theorem right down here. Okay, so take a look at that theorem. We covered that in class the other day. So for this function, we just need to verify these three things right here. We need to verify this. Well, okay, that's pretty easy. Notice that f of, In this case, my p is 0, so if I put 0 in here for x, I get back e to the 0 minus 0 minus 1. That's 1 minus 1. That does equal 0. That checks out. If I look at f prime of 0, okay, well, let's notice here that f prime for this function, let's just put that over here. F prime is e to the x minus 1, and also f double prime is e to the x. Now f prime of 0 then is going to be e to the 0 minus 1, and that is 1 minus 1 again, which gives me back 0, so that checks out. And then if I look at f double prime of 0, we get e to the 0, which is 1, and that does not equal 0. Okay, so we have a root of multiplicity 2 at p equaling 0. Now let's apply Newton's method and the modified Newton's method and see how much faster the modified Newton's method is than the regular Newton's method. Okay, so now for the modified Newton's method, remember we're going to have to, this is the function we're going to have to iterate. Alright, so it's going to be f prime, which is so now I'm going back to this formula right here. Let me just show you. Okay, so we are going back to we're going to do this formula right here. Okay. So here's my, that's actually f prime. I need to multiply that by f as well. And then divide by f prime squared. And then minus f times f double prime. Alright, so this is the function that you could plug into your calculator and iterate it. Begin with a guess. We know that 0 is a solution, so you could begin like with x equaling 1 or something. And that's, you would iterate that with your calculator and you would see how fast it converges. Now I have an Excel macro to do this, so let's take a look at the Excel macro and see how it executes this. Alright, so here's our macros. So first of all, for these macros, these are posted on Moodle. You notice right here we have 3 functions defined. The first one is f, then the one right here is, I call that df, that's actually f prime. So you notice I have exp x minus 1. That's this exp x, that's how you execute e to the x in Visual Basic. And then down here is the derivative. I call it the df function. And then right here is the second derivative. I call that ddf. So these are the 3 functions we're going to need to execute the modified Newton's method. Now here's this first macro here is the standard Newton's method. So you notice we start out with a guess. It's in whatever cell we put in the spreadsheet and we have to highlight it. So this grabs the value from the active cell in the spreadsheet, stores it into the variable p0. And then we simply enter into a for loop that executes the regular Newton's method 20 times. And see, this is the regular Newton's method. X minus f of x over f prime of x. So this is a regular Newton's method. Now down here we have the modified Newton's method that we just went over. So you see right here is this is the x minus f of x times f prime, and then all of that divided by the derivative of f squared minus f times f double prime. So this is our modified Newton's method down here. And you see once again we also start with the guess P0. We enter into a for loop and we just do it 20 times and we just keep updating. Now you notice that each time we evaluate the modified Newton's method, we just store the new variable back into P0 again, and then this line right here outputs it to the spreadsheet. You notice I output it, you see this I right here, so we output it when I is 1, for example. We output the new P0 value to the cell right below the current active cell. So if the active cell row value is currently 1, when we jump into the for loop here, the I will be 1 for the first time, so we go 1 plus 1. That of course is 2, so we will output the P0 value to the cell right below the current active cell value. Alright, so this is how the program works. You can use this for your homework. And let's see it in action, and let's see why. Let's see how much faster the modified Newton's method is than the regular Newton's method. So if we go back to our spreadsheet, let's just delete these values out here. Okay, so here's the regular Newton's method now. We're going to start with a guess of 1, and let's see how fast we converge to 0. So when we execute the macro, okay, there we go. We executed it 20 times. We did the regular Newton's method 20 times. Now you see we should get 0 as our answer. And if we look at the very last value here, okay, that's the 20th iterate using the regular Newton's method, and we get a value like 0.000001356. After 20 times, it's working. We're converging to 0, but it's not very fast. Notice we only have accuracy out to about the 5th decimal place. We should get exactly 0. After 20 iterations, that's not very good. It's rather slow convergence. Now let's see how much faster the modified Newton's method is. So if we execute that, so I highlight that one right there, and we'll run the macro for the modified Newton. Now look, after this is P0, P1, 2, 3, after like 3 iterations, this number is basically similar to this one down here. We have accuracy to about the 5th decimal place after just 3 iterations. And you notice after 4 iterations, we have accuracy to like 10 decimal places. And after that, the values don't really change. The computer has a little bit of trouble when the numbers get so small. It starts to give the computer a little bit of trouble dealing with such small numbers in the numerator and denominator of a fraction. And so it doesn't really change after the 4th iteration. Notice that this value is like, has like 10 zeros. It's like 0.000 10 times, and then 4, 2, 1, 8, 5, 9. So that's really good accuracy after just 4 iterations of this modified Newton's method. Okay, so that illustrates why this modified Newton's method works so much better than the regular Newton's method. And let me illustrate one other thing here I didn't mention. I just want to illustrate here, just to point something out. Remember that function u that we were working with before. we were applying Newton's method to this one to reduce the multiplicity of the root. Let me just give you a real easy example to understand why. If the f has a root of multiplicity 2 or more, this will only have a root of multiplicity 1. So just consider something very simple like this. Suppose f is equal to x minus 2 cubed. You notice that this has a root of multiplicity 3 at x equaling 2. Now if I plug this in here, you see it becomes a root of multiplicity 1 right away. You notice that if we plug this in here, we get x minus 2 So you see now what we get is canceling here, we get 1/3 times x minus 2. So you see we ended up with a root of multiplicity 1 at the same 0 value, namely 2 in this case. So you see that's why when we deal with this function right here, the multiplicities sort of cancel out and you end up with the u function having just a root of multiplicity 1. And that's the function that we apply the regular Newton's method to this function u. And when we plug the f and f prime in, we end up with that formula that we had earlier. Alright, so that concludes our lesson about how to modify Newton's method when we have functions with roots of multiplicity 2 or more.